here in the Breaking Things track. This morning's speaker is Rafal Wojtczuk, and his speech is A Stitch in Time.
Good morning, ladies and gentlemen. This talk will be about a very unique case of a vulnerability that affected multiple operating systems and was discovered earlier this year. So the agenda is, first we'll do a very quick high-level overview of the vulnerability. Then I will refresh your memory how exceptions and syscalls behave on x86-64 architecture in order to be able to understand the details of the vulnerability. Then we'll talk about the techniques necessary to exploit the issue. And then we will finish off with some more or less related musings, which hopefully you will find interesting. So as promised, very high altitude overview. This vulnerability has been assigned identifier CV 2012-217 and respective cert vulnerability node number. And the description of the letter goes like this: Sysret 64-bit operating system privilege escalation vulnerability on Intel CPU hardware. So, just to make it clear, it's a privilege escalation vulnerability, not a remote code execution. And the impact is untrusted, unprivileged user mode code can get kernel privileges, so full control over the machine. And the root cause of the problem is that on Intel CPU, the semantics of the Sysret instruction is a little bit counterintuitive. It happened that when this instruction is executed with non-canonical return address in RCX register, it throws an exception in ring 0. So don't worry, more details are coming. For now, we'll just keywords mode, high-level overview. And the patches were released on 12 June this year, so not a 0-day in any way. The affected systems. Once again, only 64-bit versions of the OSs running on Intel CPUs are vulnerable. So 32-bit OS running on AMD CPUs, they are not vulnerable. So Xen with PD guests is vulnerable, and that's quite notable, I would say, because as far as I know, this is the first vulnerability in the core of the Xen hypervisor that allows totally unprivileged non-driver domain to break out of the VM confinement to get kernel privileges. So really something very unique. And other affected systems are Windows 7, Windows 2008, R2, FreeBSD, NetBSD. Vulnerabilities in these systems are much more common, but still this vulnerability is pretty unique in itself, worth studying. And as you may imagine, it's not that straightforward to coordinate patches releases with 4 different vendors. All of them have different priorities, different schedules, etc., etc. So the conversation started with Xen security team, and in fact it was pretty fruitful also from a technical point of view. They have provided quite a lot of insight. Then other affected software vendors were contacted, and then the situation got a bit complicated because differences in opinion when to release patches. And then Intel, US CERT, Bromin guys tried to help, and then all's well that ends well. Every vendor has released patches on the same day, so that was the goal of the exercise. The list of non-affected systems is even more interesting. Apple OS X is not vulnerable. At least that's what they say to CERT in an official statement. I did not investigate any further. OpenBSD 5 or newer is not vulnerable. But the tiny thing is that they fixed the last remaining exploitation vector by accident during the code cleanup, not really knowing that the problem is really there. So my reaction to that was, lucky bastards, it was really close this time, right? But on reflection, when you think about it, it's not just dumb luck, right? If you reduce the entry points into the kernel, make the security critical code more uniform, then sometimes you are justly rewarded. So not really a case of total dumb luck this time. But it really pays in comparison with the Linux case, because Linux kernel developers fixed the issue consciously, purposefully, really knowing what's going on 6 years ago. They have even assigned CV number for that. So this is even more shocking. You can imagine my jaw literally dropping to the floor, because I thought I have discovered something really unique, and then I learned that this is in fact 6-year-old vulnerability. Not a pleasant experience. So the main question here is why so many systems were left vulnerable after 2006? All the remaining operating systems, maybe with the exception of Windows, were vulnerable throughout all of this time, right? And one possible explanation is some, problems with communication of the issue. Linux developers have this habit of, not shouting from the rooftops about security issues, right? They just fix it. They just, make a proper statement in Git commits, but nothing about that. And for instance, when you have a look at the CVE entry assigned for this Linux vulnerability, you see all the symptoms are there, right? The Sysret instruction is mentioned, the exception handler running on their own stack, etc., but it's still, not clear that it may affect other system. Only Linux kernel is mentioned, so it's really difficult. And also impact is not specified explicitly. So if you're a developer of other operating system, you look at the CVE entry, you see, just something Linux specific, no impact, so it's not very interesting. Even more, when you look at the security focused database and the item 17541, it's titled Linux kernel denial of service vulnerability. So apparently it was not clear for everyone that this issue is actually exploitable. And we'll see in excruciating detail that this is not only a denial of service issue. So apparently other vendors did not notice the problem immediately, were not warned in an explicit way, and that resulted in all these systems remaining exploitable for 6 years. So this is an explanation of the title of the talk. A stitch in time in 2006 could have saved 4 operating systems, right? So it's also the reason for this talk, just to make it explicit for everyone who follows some security events that the semantics of the Sysret instruction on Intel CPUs is really weird, so developers beware, right? Okay, and finally, as privilege escalations vulnerability even worth talking about, right? Because again, first you have to be on the system to exploit it, right? So on server systems, when you have untrusted users, then obviously it's very relevant, right? You don't want to allow every possible user on your system to get full control over the machine. But even maybe it's not obvious, but even on desktop systems, which are commonly only single user systems, this kind of vulnerabilities are also very relevant because they allow to escape from many sandboxing solutions. And the sandboxing are omnipresent at the moment. You have security enhanced Linux, you have Capsicum on BSD, Chrome sandbox, Adobe Reader also runs in a sandbox, and in many cases all these sandboxing solutions can be broken by abusing a single kernel vulnerability, at least a proper one. You can read on Chrome's blog about really crazy things that researchers have been doing to break out of Chrome sandbox. Like you have to chain 10 or 14 different vulnerabilities, right, to get a full bypass of the Chrome sandbox. But in fact, a single kernel vulnerability is enough. So I think it's very relevant. And also, multiple OS issues like this are very rare, so it's, again, I think worth talking about. Okay, so as promised, now we'll dive into some details about syscalls and exceptions on x86-64. I hope most of you are more or less familiar with the subject, because the chapter exceptions and interrupts occupies about 70 pages in Intel's manual, so it's impossible to do an exhaustive introduction. So just highlight a couple of most important facts required to understand the nature of the vulnerability. Okay, so the first slide is about what happens when exception is raised while we are in ring 0. So you see, okay, CS is the ring 01. Instruction pointers points to some kernel memory, and this instruction is about to throw an exception, and the stack pointer points to some kernel stack. Generally, the red color means user mode memory, the green color means kernel memory. And then if this instruction throws an exception, in this case it will be in illegal opcode, what happens? Control is transferred to the exception handler, and some information about the processor state is pushed on the current kernel stack, right? So that the handler can execute, do its job, and then possibly restore execution based on this processor context. And when you look at it, it's very similar how a normal procedure calls operates, right? When you do the call instruction, then the control is transferred somewhere, and the information about the processor state, return address, is pushed on the current kernel stack. Okay, and now case number 2, exception while we are in user mode in ring 3. So this time we are in ring 3. Instruction pointers points to the same UD2A instruction that will throw an exception in a moment, and the RSP register points to some user mode stack. Then what happens when the exception is triggered? There is something very, very different from the previous case. The first thing that processor does is to switch the stack pointer. Processor switches the stack pointer to some dedicated location in the kernel area. This address is controllable by the operating system only. And then it switches to ring 0, of course, because exception handler is running in ring 0. Then, as it previously, pushes the exception record on the stack and transfer control to the exception handler. So there's something very, very different in this case, the stack switch, right? And why is it important? We will see more details in a while, but for now, let's say it's a necessary security measure, right? Because what would happen if there was no stack switch? Just imagine for a second. And in such case, malicious user mode code could set stack pointer to something invalid. That's only one possible case of problem, but for instance, assign 0 to RSP. And then when exception would happen and there would be no stack switch, then the processor would try to push the exception record on the current stack, which points to some invalid unmapped memory. And that generally means trouble for the operating system. What kind of trouble precisely depends on the implementation, but it usually results in a double fault and system shutdown. So what processor does is first it ensures it has a sane stack, right, regardless what the stack was at the moment of the exception, and then carries on, pushes the exception record on the stack. In other words, when we are in ring 0, the current value of the stack pointer is somehow trusted, right? Processor trusts that if the ring 0 code throws an exception, it knows what it's doing, right? There is no need to adjust the stack pointer. It must point to the sane location in the kernel memory. But as you probably are aware, when the word trust appears, then things are almost guaranteed to go awry sooner or later. Particularly if we are in ring 0 and somehow stack pointer is not sane, if it's controlled by the untrusted user mode, then we must be very careful to not allow an exception to happen, right? Because if we are in ring 0, then there is no stack switch during the exception, and the stack pointer must be sane at the moment when the exception happens. And generally, it's very unusual if a ring 0 code runs with a stack controlled by the user mode, right? Stack pointer is a very crucial component of the execution state. So normally all sane kernel code should run with the sane kernel stack. Okay. Yeah. I have already said that. There is one more thing. There is a mechanism named interrupt stack table, which allows to force the task switch even when an exception happens in ring 0, right? But Intel's manual suggests that this feature should be used only for really catastrophic events like machine check exception, double fault, or NMI. And that's exactly what normal operating systems do. They don't use this feature for normal exceptions. There are problems with this approach. For instance, recursive exceptions are not handled well, etc., etc. Okay, and now let's have a look how a syscall instruction behaves. The purpose of this instruction is to enter kernel mode in an efficient manner so that the kernel can execute the system call, right? just as the name indicates. So what happens? We are in ring 3. The instruction pointer points to the syscall instruction. It's 2 bytes actually. And let's say that the stack is in user mode memory. Then when this instruction is executed, we switch to ring 0, right? Because generally system call handler must run in ring 0. But observe, again, instruction pointer is changed to the syscall handler, but observe that the stack is not switched, right? And this is really something that sticks out. At least at the entry of the syscall handler, the stack stays the same. It has a user mode value. And it works because the syscall instruction itself doesn't put any context on the stack, right? For instance, the return address, which is usually after the syscall instruction, is put in the RCX register. Yeah. But again, it's really a bizarre situation. We have a ring 0 code running with the stack controlled by the user mode. And that particularly means, as I have already mentioned, that this is a dangerous situation. Particularly, the syscall handler cannot call any higher level code functions, like C code functions, right? Because in order to call a function, it must put the return address on the stack. So the first thing that the syscall handler does, it saves the user mode RSP somewhere, and then assigns some sane value to the stack pointer, right? So as you see, the syscall instruction itself does not change the stack, but the syscall handler is tasked with it, right? It's the responsibility of the syscall handler to set RSP to some sane value. And then when RSP is sane, the syscall handler does its job, calls function, etc., etc. And then when it's about to return, again, it must restore the user mode RSP value, because the companion Sysret instruction that returns to the user mode, again, does not touch RSP. So it must restore the initial RSP value, and then issue the Sysret instruction. Okay, so again, I told it many times, if an exception was to happen in a syscall handler when RSP value is still controlled by the attacker, it would be a problem. So we may have a look at these instructions in red, because they execute with untrusted stack pointer. And is it possible that an exception will be raised? And assignments to RSP, just move instructions, right? Assuming the same configuration of the OS, nothing bad can happen. But how about the Sysret instruction itself? Again, as you see, the Sysret instruction is executed again with user mode RSP. So can a Sysret instruction throw an exception? So let's have a look at the relevant manual entry about the Sysret instruction. And as you see, there are a couple of cases when it throws an exception, but if you look closely, they are really not relevant. They can happen when the processor is too old to support the Sysret instruction, or when the Sysret instruction is executed not in ring 0, etc., etc., etc. So the conclusion is, no, Sysret cannot throw an exception. So we're cool, there is no problem here, right? Except for a tiny fact that, you see, this is an AMD manual, right? So yes, on AMD processors, Sysret does not throw an exception. But how about Intel processors? Well, everybody knows they are compatible, right? They license the technology, so it should behave the same, right? So let's have a look. And again, you see the exceptions are possible if the system is misconfigured, but then there is another very, very explicit check. If the ECX register contains a non-canonical address, so the Sysret instruction would try to return to a non-canonical address, then an exception is raised by the Sysret instruction itself, right? The GP is raised, general protection fault. So it is slight deviation from the semantics observed on AMD processors, very, very slight one. It doesn't happen in real life ever. But the impact of the slight change of semantics is total compromise of the security of the systems. Total ring 3 to ring 0 escalation. Okay, so that was a few details. Now let's have a look how precisely we can we exploit this fact that the Sysret instruction throws an exception while it is still in ring 0 mode, but the stack pointer is controlled by the user mode. Just a quick reminder again, I hope most of you know it. What is a non-canonical address? So on x86 64 systems, the pointers are obviously 64-bit long, but in fact not all 64-bit virtual address space is supported, because that would require too many levels of page tables and it would be inefficient. So instead, the pointers, you can set only lower 48 bits of the pointer in an arbitrary way. And if the pointer is supposed to be canonical valid, then the top 16 bits of the pointer must be the same as the bit number 47. It must be all ones or all 0. So there are two ranges of canonical addresses, right? From 0 to 1 shifted left 47. So all top 17 bits are 0, and the other one symmetrical at the end of the address space. All the top 17 bits are 1. And if the pointer who has a value from this black hole range is dereferenced, then the processor does not allow it. It immediately throws general protection exception. So in fact, again, the address space is 48 bits long, split into these two ranges. The valid range of virtual addresses. So why? We have seen that there is a case when the Sysret instruction throws GP exception. So why it normally never happens? Because normally the syscall instruction is somewhere in the middle of this first canonical range. So the address immediately following it, right? So where the processor tries to return is also canonical, right? So the return address is usually always canonical. But what we can do is to place the syscall instruction at the very end of the canonical address range, right? So the processor will try to return to address 1 shifted left 47 just after this syscall instruction, and that address is non-canonical. And okay, that's again. I hope you are following that. This is a problem with the exception is raised in ring 0. But with an untrusted value of the kernel stack. The tiny problem is that normally operating system reserves some range of addresses for user mode and the other part for the kernel. So the question is, can an untrusted user mode map a page and this address 1 shifted left 47 and place an instruction there and jump into it? And it happens that on Linux, Windows, and OpenBSD, NetBSD, no. Kernel does not allow user mode to map this virtual address. But on FreeBSD and on Xen with PTGuests, yes, it is allowed. So for now, let's have a look at the FreeBSD case. Denial of service is really straightforward, as mentioned previously. We map memory at this end of canonical address range at 1 shifted left 47. You place a syscall instruction at the very end of this page, set RSP to something unmapped, for instance 0, and jump to the syscall instruction. Then when the syscall handler will try to return, it will get an exception. And that will result in double fault and immediate shutdown of the system. But we can do better. We can really get code execution in ring 0. Observation is here that when the Sysret instruction throws an exception, it's actually a write operation, right? Because there will be a memory write to the address specified by the current value of the RSP register. So one possible trick is, before executing syscall, we will set RSP to point to some very important kernel structure, right? Very important kernel structure. So when GP is raised, the processor will try to store the exception record on the stack, and it means it will overwrite this very important kernel structure. And also the GP handler will start to run, because this time the value of the stack is valid and an exception record can be put on it. But any subsequent stack pushes, for instance when calling an instruction or saving a register, will overwrite this very important kernel structure as well. So again, the point is that if Sysret instruction throws an exception, it's a write instruction, and we control the address of the write, right? Because the user mode code can control the value of the RSP register. The problem is that we must select this override target very carefully. It cannot be anything, because again, usually the purpose of the GP handler when it is invoked from an unexpected location in ring 0 is to shut down the machine. Right? The kernel sees that something wrong is going on, and the sensible thing is to shut down the machine. Linux is a notable exception. It can, whenever it gets even a very fatal exception, while if it's not in interrupt, it just reports an oops in the logs and carries on. But all the other systems behave this way. Also, there is another element of the execution environment which is unexpected in this case. It's the base of the GS register. And I will not, dwell into details about that. This talk is complicated enough. But just bear in mind that there is another problem with the GS register, and because of that, in case of BSD, the GP handler will crash very soon. About 10 instructions. Whenever it will try to reference memory with GS prefix, it will generate a page fault. So again, if there is a page fault in the GP handler, it's again problem. And we should the exploit must be prepared for this situation. Okay, and the solution to all these problems is to override the interrupt descriptor table. Because IDT holds the address of the page fault handler. So this will allow the GP handler to run, will allow it to throw the page fault exception, but when the page fault exception will be triggered, we will already control the IDT. So again, to sum up the whole scenario is, it's a little bit cut. So again, we allocate memory at address 1 shifted 47 minus page size. We place a syscall instruction at the end of this region. We set RSP to point in the middle of the IDT. Then the syscall instruction is executed. The syscall handler starts to run, and when it's about to when it executes Sysret, another exception is raised. And then we arrive at the situation on the right-hand side. The GP handler is running while its stack is in the middle of the IDT. Right? So again, pushing of the exception record and any stack pushes done by the general protection fault handler will override IDT. And after about 10 instructions, the GP handler will throw a page fault, and because the address of the page fault handler has been overwritten, having overwritten the address of the kernel's shellcode, then arbitrary code execution is possible. And it happens, this is pretty reliable method. There are some corner cases, but really ignorable. And one feature of this is that we don't need any absolute addresses of kernel data structures, right? For instance, if exploit is executed in a jail, right? So we have no access to actual kernel binary, and it's not easy to determine, the exact binary version. We don't need it. All we need is the address of IDT, and it's possible to obtain it via SIDT instruction. So again, this exploit is reliable, does not require any prior knowledge, and generally this IDT override is a very generic method. Okay, so let's try to have a look if it works, really. I think at the moment there are public exploits on GitHub for FreeBSD, so it's really nothing very spectacular. But anyway, let's have a look. Where's my mouse pointer? Okay. So this is really FreeBSD 9.0. Let's find an exploit somewhere, and the user is unprivileged, right? So it's a really unprivileged user. I could run it in truth, I could run it in jail. It's it's all the same. Of course, I don't have any, slicky exploitation framework like Canvas one, so we don't have a nice GUI. All we can do is just, execute the exploit and get a hash prompt, right? And even not that, you don't get a hash prompt, but it's just the way how exploits on BSD work, how the shared credential structure is handled. We can just see that this time really we are root, right? So it really works in a reliable way. If you just type sh, then you can get your hash prompt, right? Everything is right. So again, this exploit is very reliable due to the fact how general protection fault handler behaves on FreeBSD. Okay, so the case of FreeBSD we have covered. Now, the presentation is totally gone for some reason. Okay, so this was a case of FreeBSD. Now, maybe let's start with this one. You remember that on other operating systems, particularly Windows, it's not possible to map this range of memory, this very end of canonical address range. How can we try to exploit the issue on, for instance, on Windows? Where are we? Yeah, that's the point. So, okay, we cannot map the system. You cannot map the relevant address of canonical addresses range. So maybe there's an other way to force the kernel to execute the Sysret instruction with non-canonical address. And it's actually possible, not only on Windows, but it's a general idea. And Jan Beulich of SUSE has spotted it first in Xen context. He was preparing the patch for Xen, and he has figured out that at least on Xen there is a special hypercall, and the user can control the address when the Sysret instruction returns to. Generally, there are two system calls. For instance, sysreturn, which is specific for Unix, and tcontinue, which is specific for Windows, but they both behave the same. It's a system call that provides to the kernel the whole execution contents, right? The contents of all registers, including RIP. And the kernel is supposed to resume execution at the context provided by this instruction. So that looks promising because we can set RSP in the arguments to some non-canonical address and then execute, for instance, tcontinue system call, and it will really try to return to this non-canonical address, right? The trouble is that these both syscalls do not use Sysret to return to user mode. They must use iret, and an exercise for audience to figure out why precisely. But the general idea is, so let's search, for instance, the Windows kernel for all the occurrences of the Sysret instruction, and let's see what can be done with it. And that's how I become aware of the thing named Windows User Mode Scheduler, which I had no idea it existed before. Again, the purpose of this technology is not very relevant at the moment. All that is important is that when a thread enters user mode scheduling, the way how system calls are treated in the UMS worker threads is changed. So normally when a thread executes a syscall and the syscall finishes, then it is exactly the moment when the kernel makes a scheduling decision, right? It looks, did this thread use up all its quantum of time? If no, so let's just resume its execution. If not, then I switch to another thread. Again, it's the kernel that makes the scheduling decision. But if UMS is activated, when the UMS worker thread executes a syscall, it never returns to the UMS thread directly. Instead, the context is changed to the UMS scheduler thread, which is supposed to make the scheduling decision. So this time, it's not the kernel who schedules the threads. The execution is always transferred to a UMS thread, and it is supposed to make the scheduling decision. the address of the scheduler procedure, so at exactly what RIP we are supposed to resume execution at, and the stack for the UMS scheduler procs is taken from the thread environment block of the UMS scheduler thread. So these two information, RIP and RSP, are in the user mode, and guess what? They are not sanitized in any way. So what we can do is set RIP to some non-canonical address, set RSP in this TB to anything we want, then execute any UMS worker thread, and when it executes a syscall, we'll arrive at the situation as before, right? There will be a general protection fault raised by the Sysret instruction, and we control RSP. Which is good. The only, this is before, that's what we can do. We can trigger GP handler running with arbitrary RSP. The tiny problem is that Windows uses more stack space in its general protection handler. It's obvious that Windows must use more stack space, right? So this time, this trick of pointing RSP to IDT is a bit problematic because Windows allocates more space on the stack. It will means we'll corrupt the memory above the IDT, right? During the execution of the GP handler on FreeBSD, all the stack always fits in the IDT, so it's not a problem. But in case of Windows, the stack goes out of the IDT, this memory before the IDT gets corrupted, and at least potentially it's a problem. Perhaps we can live with that, but probably it would require us to restore the memory corrupted before the IDT. Okay, so another idea, another exploitation method. Okay, let's not point RSP to the kernel mode at all. So we won't attempt to overwrite kernel memory with pushes of exception record. Let's just point it to the user mode area. So GP handler will execute with its stack being in the legal user mode memory. And we can preload it with really evil stuff, non-canonical pointers, integers that will wrap, or whatever you can imagine. So again, that's the scenario. GP handler runs with the ring 0, and the stack is in the user mode memory. So the difference this time is that we can somehow initialize this memory before triggering the exploit. That's the idea. Because again, this is user mode memory accessible for the user mode. The problem is that initializing this stack before triggering an exploit will not do us any good, because normally the stack is treated as an uninitialized memory, right? But by any sane code. Code never reads from any location on the stack before writing to it. And if you really craft a code, at least in C, that it really tries to read an uninitialized value from the stack, the compiler will warn you about it, right? And you should fix your code. So again, whatever we put into this user memory will not be used by the general protection handler. So what we need to do, we need to override some stack locations after it was initialized by the GP handler, right? But before it is actually used by it, right? We'll see exactly the scenario in a while. But what it means, we have to create a race condition. We will run another thread concurrently with the exploit thread, and this another thread will just continuously hammer at the stack locations with writes. So again, it's a race condition. We'll need multiple threads, so it works only on SMT system. So the scenario goes like this. Well, GP handler starts to run, and at some point of time it will call some function, right? This meaning that it has to put the return address on the stack that is in user mode memory that we control. This some function does its job, and then when it's done, it returns by popping the return address from the stack. And this other overwriter thread will just continuously overwrite the place on the stack when this function returns address is stored, right? So it's just a single move instruction in a loop, continuously write to the same location in the stack. And if you are lucky and this write in this thread happens while the function is executed, then we're at home, right? will write to the stack after it was initialized by the GP handler by putting the return address, but before it is used, right? So again, it's a normal race condition. We have some write by the GP handler, then we overwrite this value in our second thread, and then this overwritten value is used. And again, of course, we will overwrite it with an address of the shellcode. Again, the point is why it works, because at this stage the stack is in user mode memory. Again, it's something very bizarre. We have a kernel code that runs in ring 0, but the stack is in user mode memory, and untrusted user mode can mess with it. Okay, so does it work at all? Well, this overwriter thread must write in the very short time window, right? Depending on how many instructions this some function executes. Well, we have more or less time, but again, it's very short time window. But again, it's only one assembly instruction in a loop. Just continuously hammer the stack with the same write at the same location. And also, this thread must be scheduled to run when GP handler runs, right? Because it's just another thread. If it's not scheduled to run, if it has been, the context switch has happened and this thread is actually not running, then we don't have a race condition. But we can spawn a lot of these overwriter threads, right? Assuming we have like 4-way SMP system, then we run exploit on one core and devote all 3 other cores for this overwriter threads. And it should work, right? The tiny problem is that, again, we have only one shot. Because if we lose this race condition and GP handler goes past this place, again, its purpose will be to backcheck the machine, right? And as far as I could test, the exploit works almost 100% on the bare metal machine, right? In other words, I never saw it fail, right? It always worked for me on a real machine. But when it's running VM, which will happen in a moment, there are some problems. Very rarely, like 1 in 20 runs, it fails, which I'm not sure why it happens. But it happens. You have been warned, generally. So now let's have a look whether it works this time. So this time, again, it's a Windows machine. It's a Windows 7 system. Again, the same notorious cracker named Mortal. It's an unprivileged user. Even what we can do, even one more tiny thing, we can execute a shell in a low integrity mode, right? This psexec -l does exactly that. Executes a shell in a low integrity mode. So for instance, if you issue, it will tell permission denied, right? Because we're in low integrity mode, there is no permission to do it. And if we try to exploit it, let's see if it's work. Keep your fingers closed. Maybe. Not really. Yeah. But okay, at this moment this machine is spinning in 100% CPUs. But fear not, I will try to show it on the bare metal machine. It's supposed to be more reliable. Anyway, that's denial of service exploit demonstrated. This RDP session is dead at the moment. Okay. So I'll show you that exploit on Windows in a moment. Let me just shut down this machine until it burns down all the cycles. Yeah, you can even see that it's somehow corrupted. Okay, so we'll continue with Windows 7 demonstration at the end. 15 minutes left. Okay. Okay. Some related research. There's a really fantastic article by Derek Sutter named VMware Emulation Flow x64 Guest Privilege Escalation from 2008. And it discusses very similar issues, right? Which were possible to trigger only on VMware when it was doing the binary translation. But again, the situation was very similar. That how to exploit an exception handler triggered in an unexpected location. And there is another CVE item for BSD, 2008-3890 by Nate Eldridge. Again, the problem was very similar. There was an exception thrown by the IRET instruction. But in both these two cases, the exploitation method was totally different. They both focus on abusing the desynchronization of the GS base. And again, I'm totally, skipping over the subject of the GS base. You can have a look at the paper on the conference CD if you want more details, or just have a look at these two articles. Because in this case, it's more important that untrusted user mode can control the stack. And it's thinkable that this Sysret issue can be also exploited by properly abusing the GS base thing, except that, for instance, Xen does not use swap_GS at all. So the method of messing with the GS base would not work in Xen case at all. There is another thing, because control of the stack gives some very special abilities for the attacker. We'll talk about it in a second. Okay, so some related musings. We'll start with a nice and cozy Witchhunt. So generally, whose fault is it, right? So many operating systems, it looks like that for each of them, including Linux and OpenBSD, at a certain moment of time, every 64-bit system was vulnerable, right? So it's really unusual. So I'll give you three answers, three viewpoints, and your task is to find the one that is actually a joke. So the answer number one is the all fault of these security researchers, right? They are leeches, right? The world would be generally better without them. I guess you recognize these quotations. So no security research, no security problems, right? That's a very interesting viewpoint. Another possible answer, how about OS developers? Really, the semantics of the Sysret instruction is explicitly documented in Intel SDM. We have seen excerpt from it. Really, you should know the behavior of the platform you write operating system for, right? You should read the manuals. And additionally, after the Linux problem 6 years ago, well, theoretically, all developers could just, get to know all the details and check whether it applies to their OSs, right? So that's another viewpoint. And the third one, how about Intel? Because frankly, allowing the Sysret instruction to raise an exception with the user-controlled stack is a design error. It frankly doesn't make sense at all. It is somehow coherent with the behavior of other instructions that throw general protection fault. But again, raising an exception while the stack is untrusted is really a bad idea. And similarly, you can imagine that in a perfect world, after this Linux case, Intel would realize the problem. There are really clueful people in there. And he could try to notify everyone, just like Intel tried to help with this case, and perhaps update SDM with an explicit warning, right? That really this semantics is dangerous. So developers should be really given a chance to notice the problem. Okay. Another issue is how about mitigation, right? So we have some, execution context corruption in the kernel. So it doesn't mean that it should ultimately be exploitable, right? And there are various mitigation techniques which are thinkable and implemented, but I would like to talk about a particular one, maybe about two of them. The first one is named SMEP, Supervisor Mode Execution Prevention. It was introduced, a year ago or something like that in the Intel manuals, but as far as I know, the first platform that actually support this feature is the third generation of core processors Ivy Bridge list in the second quarter of this year. So very, very new thing. And this feature would prevent both these exploitation scenarios that were presented, right? Because in both these cases, the goal of an attacker is to execute arbitrary code, which is stored in the user mode page with the kernel privileges. And why it is stored in the user mode page? Because it's a convenient location. You know the address when your shellcode is. You can really initialize it any way you like. So it's a natural choice for an exploit. Run the code that is stored in the user mode page. And this SMEP feature prevents exactly that. When kernel mode code tries to jump into the user mode page, then exception is triggered instead of allowing to execute this potentially untrusted code. So that sounds nice. Again, it would prevent both these attacks. And for instance, Xen turns on SMEP by default since a long time ago. But the problem with this mitigation technique is it's very similar to NX and DEP, right? Because both NX and DEP, what they do is disallow execution of data pages, right? And that's very similar. Do not allow execution of pages which should not contain the code you are supposed to execute. But again, very similar bypass techniques are applicable in this case. We can use return-oriented programming not to run arbitrary code stored in the user mode pages, but just to jump through the location in the kernel code. There are a lot of publications about return-oriented programming, really, so you can deepen your knowledge in that aspect. But it's really a step in the right direction because it's bypassable, at least in the general case, but it really makes the life of an attacker more miserable because he has to know the exact version of the binary of the kernel, right? He has to know exactly the addresses of the useful functions in the kernel. In some cases, for instance, if I were some cloud services provider and I build my own Xen version and it's not published anywhere, it may be very difficult for an attacker to obtain the addresses of useful code pieces in the kernel. So again, something bypassable, still a step in the right direction, but that brings us to the final point, lessons learned, right? To the state of the mainline kernel security. And again, it's my gut feeling only, but not only mine, that there are really problems with the current mainline kernels. And there are reasons for that, because these kernels are very large, monolithical pieces of code, right? And you have large pieces of code that all runs with the high privileges. In ring 0, it implies many vulnerabilities. And it happens they're often reliably exploitable. And the reason for that is that there is insufficient separation between kernel mode and user mode. At least that's the impression of many people. For instance, the virtual memory is shared normally, right? And this is the reason why it is so easy to store kernel shellcode in user mode, and it will be valid when we are in kernel mode, right? It very simplifies an exploitation. So again, it's obvious that, for instance, Intel tries to provide some tools like SMEP, which again make exploitation more difficult. But in fact, my feeling is that it's really attacking the problem from the wrong end, right? A lot of people have simply totally gave up on kernel security, and instead people are trying to use other mechanisms, for instance based on virtualization, to totally encapsulate the untrusted code within the VM, and that way provide some sort of sandboxing to limit the damage that happens when the issue is exploited. So particularly, we saw this FreeBSD exploit a moment ago, and in fact it was running in the VM, right? So if it was really malicious code, then theoretically, in a perfect world, no harm should be done to the host operating system, right? So you know the statement: what happens in Vegas stays in Vegas, right? So perfectly, ideally, it should be what happens in VM stays in VM, right? You can get ring 0 privileges in VM, but again, we shouldn't care because you are sandboxed. Yeah, so again, hardware-assisted virtualization used for sandboxing has a lot of potential, at least in my opinion. Okay, that's almost all. Please provide feedback to organizers. We have 5 more minutes, so we will skip the topic of Xen. I have an exploit for Xen as well. It's quite reliable, but it's very specific for Xen. So these 2 previously shown techniques, so overwriting of IDT and raise condition over the user mode stack, are very generic and should be applicable to other systems. But Xen case is very specific. They use the stack pointer in a very special way. But just believe me, it's totally exploitable. And also I saw yesterday that the company named Wupen, which provides exploit and analysis for some government clients, has also announced that they have released exploits for all the affected systems, for Windows, BSDs, and Xen. So these issues are really exploitable. Okay, again, we are almost done. So let's try to run the Windows exploit on the bare metal. So no, we won't have any Xen demonstration. Yeah. Okay, so this runs on the bare metal. Do you see anything? I can try to make the font larger. Right, 3 minutes left, plenty of time. This one, slightly better. Okay, so as before, let's try to -L. Crap. It pops up a non-privileged shell in low integrity, but here, okay. And now again, all we do, run the exploit binary and pray it will work this time. Yeah, it works. Again, the problem is it's an extended desktop and it pops a shell on the other desktop. Here it is. This time it runs as a system. Right. Sometimes it works, right? Again, on bare metal, I have never seen it fail. There is some issue with scheduling within the VM. I am not sure what's the reason. Again, I'm pretty sure it can be improved. Okay, so very quickly, questions. We have like 2-3 minutes left. Any questions? No? Okay, that should be it. Thank you.